So, viewer, what's the highest number you've counted to in one sitting? Me? Well, I think it's just about 200. I rarely need to go higher. I do know that Mr. Beast famously counted to 100,000 and that Jeremy Harper counted to 1 million, but what's even the difference? Yes, the numbers are different and it takes quite a lot longer to get to 1 million, but when you think about these numbers in your head, do they really have that much of a difference? Okay, fine, here we have a difference of 40 hours and 3 months of time spent counting, but a million and a billion? A trillion and a quadrillion? Humans, as creatures that exist in a world of nature, never needed to evolve to understand concepts of such scale. In fact, we made up the concept of counting ourselves to make it a bit easier to understand the difference between one predator, a potential source of food, and 3 predators, almost certain death. Sure, as we evolved, we needed to improve our mathematics for the sake of progress, but we never really understand the numbers we are working with. The largest conceived number that can exist, that being the amount of atoms in the universe, is so far beyond our comprehension that our only real way to understand it is to show it as this and then work our way down. This is 10 to the power of 80, which is 10 times bigger than 10 to the power of 79, which is 10 times bigger than 10 to the power of 78, and so on. When you see those videos that show the scale of the universe, what do? Well, they show you a point of reference and go up and up. The trick to visualizing such scales is recursion. Functions will be how we ascend the chain of numbers to eventually reach the peak of human conception. There are a few to choose from, but for this video I will use BEAF, also known as Bauer's exploding array notation. Before we get to it though, we can start with recursion that you're already familiar with. 3 plus 3 plus 3. This is obviously 9, so where's the recursion? Well, we can write 3 plus 3 plus 3 as 3 times 3, and here we see an interesting difference. As we will climb the ladder of ever-increasing numbers, you will realize that increasing the size of a digit and going from 1 to 2 is a very slow way to reach big numbers. So if we go from 3 plus 3 plus 3 to 3 plus 3 plus 4, that's a difference of 1. But if we go from 3 times 3 to 3 times 4, well, that's a difference of 3. When you want to go bigger, you don't just increase the number, you create ways to grow them faster. And so, we continue to 3 times 3 times 3, which is 3 to the power of 3. Now, this is where most people would stop with big numbers, and it's a reasonable place to do so. Even in mathematics, a lot of big numbers are described in powers of 10, with our previous example of the amount of atoms in the universe being just that. This is why you've likely never heard of ways to go bigger. But don't worry, we're just getting started. This is where we introduce our first new notation, Knuth's up arrow notation, or just arrow notation. Here we have a new symbol, the up arrow. You may think it's similar to this symbol of exponentiation, and it is, because 3 up arrow 3 is 3 to the power of 3. But what about 3 2 up arrows 3? Here, I want you to once again think about recursion, because 3 2 arrows 3 is 3 arrow 3 arrow 3, which is 3 to the power of 3 to the power of 3. This can be simplified to 3 to the power of 27, which is about 3.6 trillion. You see just how much powerful we can get if we go up a layer? We just went from 27 to 7.6 trillion. So the question is, what is next? Well, of course, it's 3 3 arrows 3, which is, as you guessed it, 3 2 arrows 3, 2 arrows 3. This means that we now have 3 2 arrows 7.6 trillion. And this is where we really start to go out of control. The way that these arrows work is that the first number is what will get repeated, and the second number is how many times it will repeat. For example, 3 3 arrows 3 split into 3 3s separated by 2 arrows. This means that we now have this massive tower of 3s, which has 7.6 trillion 3s in it. Obviously, this number is, well, big, but of course, we can always add more arrows. 3 4 arrows 3 is 3 3 arrows 3 3 arrows 3, which takes the value of this tower to be how many 3s there are, and so on. What I want you to keep in mind isn't how the arrow notation works exactly, since it usually takes some time before it sinks in. Instead, I want you to keep in mind this idea that we are climbing up, and that if you ever want to try to understand how big something is, you can look down a level and find your way to numbers you can still comprehend. As for where we go next, well, writing more arrows is cool and all, but it takes up quite a lot of space. This is where we come back to that BEAF notation I mentioned earlier. We start by simplifying our expressions, and instead of writing 3 arrow 3, we write 3 1 3. Here, the same idea applies. The first 3 shows what we are repeating, the second 3 is how many times we repeat it, and the one in the middle shows how many arrows we will put in between. So 3 arrow 3 is 3 1 3, 3 2 arrows 3 is 3 2 3, and so on. Obviously, the convenience here is that we can now easily put in however many arrows we want without having to fill up the entire page with arrows. But while 3 103 is cool and all, because it's so far beyond just about anything useful ever made in mathematics, it's still infinitesimal to our next step. Remember, if we want to go even higher, increasing the digits won't do us much good. That's way too slow. So instead of writing 313, which still means 27, what if we wrote 313 surrounded by 2 brackets? What this does is it takes the second 3 and creates half plus 1 copies of it with 1 less bracket. So we get 3, 3, 3, 3, 3. What does this mean? Well, again, use recursion to climb down. 3, 3, 3 is 3 3 arrows 3, which is that big tower from before. This means that we then have to take this number's value, which is ridiculous, and that's how many arrows will be between this 3 and that 3. And now we are finally starting to get somewhere, because we cannot even fathom the start of this number or the start of this number. I can maybe understand that this stack of 3s goes on for a very, very long time, but that many arrows? That's not comprehensible whatsoever. Of course, BEAF has no intention of stopping there. We keep using 1 in these functions, so what happens when we make it a 2? Well, something unimaginably bigger, of course. 3 2 brackets 2 3 splits into 3 2 brackets 1, 3 2 brackets 1 3, where the second number says how many 3s will be here. So now we take that incomprehensible number and put it on the right side of the brackets, making it 3 double brackets 1 to that number. Climbing back down, this means that we will have 3 bracket 3 bracket 3 bracket 3 bracket 3 copies of that insane number, which is, well, do I need to say it? For me, this is the point where it stops really mattering. Okay, yes, this is big, but why? You can't even begin to comprehend this number, so why have it? This is why BEAF continues on simplification, because conserving space and quickly growing is what matters most. Making sense to mortals like us comes after. If we continued on with so many brackets, it would get quite annoying to write out these numbers that no one can imagine, so this is where we come to the linear array notation. 3 3 1 2. Here, the 2 3s are the same as usual, the start and the end. The 1 is the number inside the brackets, and the 2 is the amount of brackets, meaning that this is equal to 3 2 brackets 1 3, that big number from before. Similarly, we can come back and write our previous numbers using this notation. 3 arrow 3 is 3 3 1 1, 3 double arrow 3 is 3 3 2 1, and so on. Okay, let's take a break, because we have finally arrived at a somewhat useful notation strategy. You can pause here if you want to look at the notation so far. Something I haven't yet mentioned is that this video was inspired by a video called Numbers from Zero to Absolute Infinity. I watched this video with some friends, and while doing so, I kept looking up the meaning of these numbers and just how big they were. I think that a lot of people enjoy the names more than that, and well, I did relate to some level, but I also found the idea of changing a 1 to a 2 to get an unimaginably bigger number was just cool. Back then, I didn't really understand that much, but hey, at least I tried. Listen, I don't actually know what a pound is.
Okay.
But what I do know is when it says a pound is very big. Very
It's
big.
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 It's
like,
big.
it's big.
It's
big. It's
big.
so big. So look, this is why in this video, I want to give you an idea of just how big and ridiculous these functions are, even if I probably won't be able to explain them properly. There are a lot of different notations you can use to try and comprehend the scale of these concepts, but it's surprisingly difficult to learn them. So, I hope you are still at least partially keeping up, if not in the explanation, then at least in the difference between the numbers. But just in case, let's quickly review. BEAF, or the linear array notation, uses 4 numbers: a number that will be repeated, a number that will say how much it will be repeated, a number that shows how many arrows there are, and a number that shows how many brackets there are. Multiple brackets split down to less brackets with more copies. Singular brackets show how many arrows there are. Multiple arrows split down to less arrows with more copies. Singular arrows show how many times a number is multiplied to itself. And all of this is written in a fairly simple to understand notation of just 4 numbers. Now, believe it or not, we are already 40% of the way through the Numbers from Zero to Absolute Infinity video. However, this is where things get a little weird. Let's say we have this number, 3312, which you may remember to be 3, 2 brackets, 1, 3. So, what do you think happens when we write 3312, 2? While there is an explanation that can show why this happens, it's a bit too technical for my liking, so instead, when we go past 4 numbers, I, again, want you to think about recursion, as we are still doing that. With this number, what happens is that we find a 1 inside the array, and in it, we throw in our current array, so this. You may notice that we have lowered some numbers, and for the inner array, we lowered the second or later number by 1, and for the outer array, we lowered the number that comes after the inner array. So if you continue on this path, this is what you reach. I think I'm not actually that good at this. Now, another rule is here to help us out. If the second number ever reaches 1, the array turns into the first number, so we can drop down a bit. And so we climb up again. And now we have 1s at the end of the 2 inner arrays. This means we can drop them because a 1 at the end means nothing. Okay, now we can turn these into actual numbers. So what's the point of all this? Well, by doing this massive expansion, we reduced this from a 2 to a 1. We'd now have to expand once again to reach the 5th number, and once that is done, we will fully unveil the answer in a notation we can understand. Obviously, at this point, I don't expect you to understand what I am talking about, but again, I do hope you can see how just by adding one more number, we go up an absolutely ludicrous amount. This is why our next symbol is so completely absurd, the array symbol. What do you think 3 array 3 means? Well, it's actually relatively simple. It's 333, which is 3 arrows 3. Therefore, 3 array 10 is, well, 10 threes, which is, well, a really large number. Welcome to the world of multi-dimensional arrays, where arrows were understandable, brackets were confusing, and linear arrays were difficult. Multi-dimensional arrays go into their own league because, well, do you really want to do this whole expansion process for this? But of course, we're just getting started, because instead of writing 3 array 3, we can write 3 double array 3, which is this. What does the 2 do? Well, after you simplify this, you now take these two numbers and make an array of them. So 3 array of 7.6 trillion, which is 3,3,3,3,7.6 trillion times. I don't even know what to say anymore, to be honest. Of course, we must climb higher, and we all know where this is going. This 3 must go higher. Actually, no, not even that. Listen, we've been at this nonsense forever at this point. Why are we still going up from one number to another? Instead, let's just put an entire goddamn array in there, so 3 array of massive array 3. Obviously, this is, again, taking up a lot of space, but we can write this as 3 array of 1.23, where the 2 says the order level and the 1 says the array level. Still, this is just taking up way too much space, so to those of you who have made it this far, please welcome 33 parentheses 112. Here, believe it or not, this 1 is not a digit in the array. It's a line break, and it shows where to separate the two arrays and write them as a two-dimensional expression. The first line will be the two 3's that we have as usual, or an array we need to simplify, while the numbers below will show how many times we need to stack these things into endless arrays. This is dimensional array notation, and this is where my ability to work things downwards recursively kind of breaks down. It's not impossible, but dude, I need this video out in a week, and I don't have the time and energy to sit through this insanity, or to try and somehow explain it to you. If you are curious to try and figure it out, I've left some useful stuff in the description that will hopefully help you out, though be prepared to give up. Thankfully, understanding this makes it easy to understand this, because if a 1 shows a break between rows, a 2 shows a break between planes. Yes, we now have a cube as our notation. Therefore, a 3 will show a break of cubes and so on into hyperdimensional arrays. By this point, I'm not asking why we are doing this anymore. I'm asking why I am doing this. I would say that the numbers here are so large, but let's be real here, they've been unimaginable back during the good old up arrow days. Yet we are only halfway into the godforsaken video, so let's quickly go through the rest of the BEAF notations. This whole dimension thing can be described in something called X structures, where the point is that 2 dimensions are x2, 3 are x3, and so on. Therefore, what is xx? Well, that's 330112. Add another level and another power goes on. Way too slow though, so instead of writing endless amounts of brackets, we write a square bracket 1, which means that we throw that X structure into an array like this, maybe, I don't really know. Stack the square brackets up and you'll have something like XX array of 100. Once you've run out of space, we start with legions, but no, we just write a slash and we continue, alright? Look, it's a slash, it's way bigger, like way bigger, and now we have a tetrathoth? What? A hyperathoth? Nucleus? Teratrom? Kopatophplex? Unadep? Oh, guys, what's up? What are y'all doing here? Oh shit. What? What do you mean with big numbers? X structures, legions, what do you mean? Just trying to go through the concepts of BEAF. Wasn't that 2 days ago? I don't know what happened back there, I just kind of woke up on the floor yesterday. Anyway, our next big number, according to the Googology wiki and the video, is Gonguldius, which is 10, 100, 1, 2 array of 10. That's not so bad. I think that's, that's 10 repeated 10 2 brackets 1 100 times in an array, so 10, 10, 10, 10, 10,
I mean,
10, 10, 10,
it's pretty
10,
big,
10.
but it seems somewhat understandable. Oh, they mean this is smaller than dimensional arrays. What are those? I'm just following the wiki here, and they clearly know what's bigger and smaller. A next big number will come from increasing the length of the array. So, heptadecatrix is a 10, 10, 10, 10, 10, 10, 10 array of 10. And 10, 10, what? Why are the parentheses there? Well, whatever, I guess we continue. Tetraculus comes in with 4 array of 4 array of 4 array of 4, so okay. So we're stacking arrays, alright. And it seems like this slash shows how many stacks you have, so you can write the same as 4 slash 2. Next is something called Taranovsky's C's. Yeah, that's pretty big. Anyway. Let's continue. So, what was the point of all this? Did you learn anything? I mean, I hope you did. It's kinda cool, even if it is pretty confusing. We are not yet done though, even if we have surpassed BEAF notation. In fact, we have surpassed all notation and have arrived at the level of uncomputable numbers. Now, I'm not smart enough to tell you why a Turing machine can or can't compute these numbers, nor do I know how to explain to you the size of Bigfoot or fish number 4. However, I can at least give you an idea on what the peak of this madness is. In the Googology wiki, there is, after all, a number that is the biggest, and it is far larger than anything else cardinal on the site. However, it does not use BEAF to be so large, nor does it use any other function on the site. This is because we can't define any function that can describe this number. The definition for Oblivion is the largest number defined using no more than econgulous symbols in some k-gongulous system, where econgulous is this and egongulous is that. The values of these numbers, beyond being extremely large, don't particularly matter. What matters is the idea that the number is defined in a system. Think of it like this. In standard mathematics and the BEAF notation, we've had a lot of different symbols, but when you put them all together, there are merely 23 symbols that we have used throughout this video, and the largest computable numbers we have conceived of can be described in these symbols or even less. So instead of us adding another symbol, what if we theorized that there was some number that could only be achieved when we perfectly used 100 symbols? That would mean that we would have another 77 symbols that would further expand the BEAF notation, for example. What about 3 up arrow 3 symbols, 330112 symbols, a congulous amount of symbols? While this explanation is simplified, that is what Oblivion is. It is mankind going on a level above their own notation. But it is not the largest number. That title, well, it doesn't really exist. After Oblivion comes Utter Oblivion, the largest finite number that can be uniquely defined using no more than Oblivion symbols. And this is the officially recognized largest number on the Googology wiki. But why not go beyond? Ultimate Oblivion is a number defined with utter Oblivion amount of symbols, and it shows that this process can be repeated indefinitely, just like how you can always add a 1 to a number to make it even bigger. In the end, we have not and will never reach infinity, even if Oblivion gets us as close as we will ever need to be. In a way that is rather disappointing, but at least this video reached its conclusion. But that was because I had to someday finish it, just like how people had to one day stop making functions. Or did they? Infinity is a concept of an unending amount, and to that end, Oblivion and its derivatives are the largest numbers.
However, if we didn't care about matching every number with an equal amount of things, we could instead care about their order. Ordinal numbers are not the same as everything else in this video, cardinal numbers, and you should remember to treat them as such. Ordinal numbers represent the order that numbers go in, not their value. The first ordinal number is not 1, it is first, then second, third, fourth, 98th, so on. What's useful about these numbers is that they have an interesting property when it comes to infinity. They are not limited by it. Let's say we had lines whose size and distance in between got smaller and smaller as we drew them. Eventually, the lines would have to stop at some point on this screen because they would get too small to make a meaningful distance. However, there is still an infinite amount of lines here, and Oblivion is somewhere in here. All cardinal numbers must be represented in one of these lines. So, what if we drew another line after all of them? Because this is an infinite set, we can always start from this line, make it represent 0, and then continue. We can even make another infinite set here and divide the two sets to represent all values of every line, because infinities are infinite. But when we use ordinal numbers, we can say that all numbers go in order, and then comes something new, something after infinity. It's not the second, fourth, 98th oblivionth number, it is called omega. Omega plus 1 comes after, then omega plus 2. Having this, we can count on and on and on, and you may find a pattern here. After all, we can continue counting till omega plus oblivion, and then we can just say that omega plus omega comes next, then omega times omega, then omega 4 arrows omega. Once we are satisfied, we can claim that some ordinal number comes after every omega with every omega iteration. Omega 1. Exhaust omega 1 and go to omega 2, then get to eventually omega omega, and define theta. These are called inaccessible cardinals, and while the cardinals we talked about at the start of the video could always be reached from below, that was the whole recursion idea, these simply can't. And this idea can extend, well, infinitely, as we can always create a symbol to break another limit of another symbol. In the end, there is absolute infinity, which is defined as the limit of all transfinite ordinal numbers. It is defined to not be reachable through any amount of replacement and can therefore never be reached. It is, ironically, implied as a number that is infinite, where nothing comes after it. Not because there really is nothing after it, but because the designer of this number decided so. Ultimately, we decide what mathematics are. Unsurprisingly, you may find a lot of people disagreeing with such a concept. However, my goal here wasn't to show you how to get there. It was to show how we will forever try and fail to do so. Then again, the mere idea that we can define things so far beyond anything the universe will ever contain is worth something in my and maybe your mind. And as always, thanks for watching.